Okay, so welcome to Abstract Algebra Math 355. I think this is lecture 12. And so we're now moving into chapter 5. So chapter 5 is going to be on fields. And then we're going to do the split today. So today I'm going to be doing the theory in section 1. And then in section 2, I will talk more about some of the motivation behind why we actually care about problems like this, as well as how to do some coding. So this is the 21st century. If you do not know how to code, you're at a tremendous competitive advantage. The computer can do so many calculations for you so quickly that you want to learn how to use it. Not just for doing calculations to solve a specific problem you know, but to gather data and use that to help you make a conjecture for what the answer might be. So you're always welcome to go to both sections. I will post the video, and if you have questions about coding, you're always happy to chat. Okay, so we've seen, I believe, fields before. So as always, we have a commutative ring. And so a field is going to be a commutative ring with the property that for every A and F, if A is not 0, then there is some B such that A times B equals 1. So here, 1 is the multiplicative identity. So which property that a group has does the ring not necessarily have for its multiplication? Inverse. It doesn't necessarily have inverses. It might have inverses, but it doesn't have to. And so if you're a field, we want to have multiplicative inverses. But 0 is not going to have a multiplicative inverse unless you're in what setting? What's the 1 times 0 can have a multiplicative inverse? There is one example where 0 does have a multiplicative. Yeah, if you consider the set that's just the 0 element, then 0 is the multiplicative inverse, it's the additive inverse, it's everything. There is nothing but the 0 element, so 0 times 0 is 0. And everything still has a unique inverse. Okay, we're not really going to spend too much time studying just the 0 set. So for us, we want to have invertible elements under multiplication. We know that we are not necessarily going to be able to invert everything because we have the multiplicative identity of 1. Okay, that's not a problem, but we have the additive identity of 0. That's going to cause some trouble. So for the field, it's if you take away the 0 element, everything else should be invertible. We've seen situations where non-zero elements are not invertible. Can someone give me a situation where the non-zero element that's not invertible? So matrices is 1. So if I give you a matrix whose determinant is 0, the matrix does not have an inverse. Or I could give you a matrix with integer entries, and it might have an inverse, but the inverse might not have integer entries. But maybe we could then extend the field and it could be invertible. Or extend the set and it could be invertible. What's a situation where you have non-zero elements that are not invertible other than matrices? Matrices is a good one. Matrices is one of our 3 go-tos. The clock. So whenever I ask you a question, you should be thinking Z clock matrix, right? You get to choose which order you want to think about them, but you should be thinking, let's see if one of those gives me an example. So if we look at a clock with 12 hours, then 3 and 4, in fact, anything that has a common divisor with 12 is not going to be invertible. Because if I multiply 3 by anything, it's going to be a multiple of 3. There's no way it's going to have a remainder of 1 when we divide by 12. Okay, so next is definition 5.3. Let R be a commutative ring. The unit group of R is the group R star is the set of all A and R such that there is a B such that A times B equals 1. Typically, how would we write B? How would we denote the element B? Yeah, normally we write A inverse. So normally we write A inverse for B, and BA equals AB equals 1 as its commutative. And so we can look at some examples. What would Z star equal? So what are all the integers such that there is an integer B such that AB equals 1? 1. So does anything other than 1 work? Does anything else other than 1 have an integer inverse? So I want an integer such that when I multiply by another integer, I get 1. So can you give me an example? So give me an integer. 2. What's the inverse of 2? 1/2. So that wouldn't work. Give me another integer. 3. What's the inverse of that? Okay. So are there any other integers other than 1? Think about negative numbers. Are there any negative numbers that might have an inverse that's an integer? Negative 1. So here we would have 2. It would be -1 and 1. Those would be the only ones that would work. What if I looked at the rationals and I wanted all the rationals that were invertible, and they have to have a rational inverse? So what would that be? So you want to try it? All of them except for 0. So there's many ways to write it. You could write it as the set of all A over B. A, B are in Z, and A, B do not equal 0. Or you could write it as Q minus 0. Similarly, we could look at the reals. What if I looked at Z mod MZ star? So this would be all the A in 0, 1. Oops, let's not do 0. All the A in 1, 2, ... m minus 1, such that, so which A will be invertible? So I'm looking at integers in Z mod MZ. So it's going to be somewhere from 0 to m minus 1. I want it to be invertible on the clock with m hours. It can't be 0. Which A's will be invertible? Excellent. So it's all the A's such that the GCD of A and M equals 1. And the proof is the Euclidean algorithm. There exists, say x and y, such that ax plus by, plus my is the GCD of A and M. So this is the Euclidean algorithm is one of the greatest algorithms we have. It's constructive, it's fast. You give me any 2 numbers, and I can find 2 more such that this expression ax plus, in this case, my is the greatest common divisor of A and M. Well, if A and M equals 1, if the GCD of AM equals 1, then we have AX plus MY equals 1. So AX is congruent to 1 mod M, so A is invertible. And that finishes the proof. So the Euclidean algorithm is absolutely wonderful. Now, if M is a prime number, then it's really easy to figure out the structure of this. Because if M is a prime, then everything from 1 to M minus 1 is relatively prime to M. It only gets hard when M has factors, and we have to just exclude things. So if I give you 12, the only things that would work would be 1, 5, 7, and 11. So Euclidean algorithm is one of the key results. We've seen it time after time after time. It allows us to analyze things. All right, and so a field is a commutative ring with the property that every non-zero element is invertible. So what this is telling us is if M is prime, this is a field. So that's a nice example of a field. So we now have some more examples of fields. We have the real numbers, we have the rational numbers, we have Z mod PZ star. And the question is, are there other fields? Is there more than just this? So we have the reals, we have the rationals, we have Z mod MZ. These are all going to be fields. The non-zero elements are invertible. What about the integers? Is the integers a field? Are the non-zero elements invertible? Not in the set. So does 2 have an inverse? Yes, but does that inverse live in the integers? No. So if I just look at the integers as my set, then it's not closed under inverses. The inverses don't live there. So this is one of the properties people forget to check all the time. You have to make sure, do the inverses live in the set? It's not enough that the inverse exists, they have to live in the appropriate place. Okay, so the next is let F and K be fields. They often use K for corpse, K-O-R-P-S. I'm not even going to try to pronounce words from foreign languages properly. And let phi be from F to K be a ring homomorphism. So what does a ring homomorphism mean? What are the 3 properties to be a ring homomorphism? Sends 1 to 1. What else? We've got 3 people here. Addition. So phi of a sum is the sum of the phis. And phi of a product is the product of the phis. I love simple phrases. Phi of a sum is the sum of the phis. Okay, so we're assuming that we have 2 fields and we have a ring homomorphism between them. The first is the map is injective. That's kind of nice. So to be injective means that if you have 2 different inputs, they can't be sent to the same output. And then the second is, given any invertible element, phi of A inverse is phi of A inverse. Why do I have to assume that A is an F star for part B? Be more vehement, be stronger. Because only A in F star has an inverse, right? If A is not in F star, what must A be? A has to be the 0 element, right? So basically part B is just saying, choose any element that's not 0. Well, if it's not 0, then we know phi of A inverse. Okay. So which do you think is easier, A or B? I think B is easier. So let's do B. And again, it's not that I don't care about you, but I've deliberately not thought about these proofs so that you can hopefully see the thought process as I do this live. So we want to show that phi of A inverse equals phi of A inverse of that. So which property of the ring homomorphism do you think is going to be the most useful? Multiplicative. So we know, for all x, y in F, phi of xy is phi of x, phi of y, as phi is a ring homomorphism. I don't need to assume x and y are in F star. I might want to take that later on, but I know just as a ring homomorphism. So I'm starting out by writing down what I think is going to be the most useful property. It somehow feels logical that I should be using the multiplicative property. I now get to choose what I want x and y to be. Any suggestions on x and y? A and A inverse, right? If I take A and A inverse, what is x times y going to equal? 1. That looks like that's going to be nice. So now take x equals A, y equals A inverse. I assume nobody would take x to be A inverse, right? Okay, good. Just making sure that we're all, that we have x is A, not A inverse. We got standards in this class, right? Then we get phi of A inverse is phi of A inverse. But as A inverse is the identity, and phi of 1 equals 1, then phi of A inverse equals 1. Now, at this point, I can be a little bit more pedantic if I want. When I say A times A inverse equals 1 and phi of 1 equals 1, are these all the same ones? No. I could, or maybe even should, write this is 1 sub f, trying to write it as small as possible. And then this would be 1 sub k. The identity in F is sent to the identity in K. Well, we know phi of A times phi of A inverse is 1. So we've just shown the multiplicative inverse of phi of A inverse is phi of A, or the inverse of phi of A. I'm sorry, the inverse is this how I want to write it? Yeah. So phi of A inverse is phi of A inverse. So, okay. Oh, so I'm sorry. I think I wrote it the wrong way. Okay, so we're looking at things in terms of phi of A. Sorry. So the multiplicative inverse of phi of A is phi of A inverse. I thought the book wanted me to prove it the other way around. Okay, sorry. So the multiplicative inverse of phi of A is phi of A inverse. So the inverse of phi of A is phi of the inverse of A. Just putting the parentheses in the right way. You can also show, what do you think phi of A inverse would be? The inverse of phi of the inverse of A is just phi of A. Right? We've just shown that phi of A equals phi of A inverse. If you take the inverse of the inverse, what do you get? You get back to where you started. So that's B. So now we have to prove A. So we want to show it's injective. What does it mean to be injective? Every element maps to a distinct. So we have, to me, the most natural way to try to prove this is to say, well, let's take two different elements and assume they get mapped to the same thing. Can we get a contradiction from that? Let's do it on next page. See next page. Okay. Proof that the ring homomorphism phi from F to K is injective. So assume phi of X equals phi of Y must show phi of X, must show X equals Y. So any thoughts about what we can do here? Do you think part B is useful for part A? Wait, before that, do you think part B is useful for part A?
No.
Why not?
Because part B is for A.
But that's fine. I mean, we know that phi of 0 goes to 0. Do you think part B is going to be of use in part A? This is just trying to use some logic about how textbooks are written. So almost surely, and again, this is not how life works, but if you're reading a book, if there's a part B, probably you don't need part B to prove A, or they do B first. Now, maybe you can prove part B by using A. Maybe if we know that phi is injective, you can then use that to get B. And we might have another way of proving B from this. But again, I'm just trying to give you, how would you think about a problem like this? Probably B is not useful to solve A because it's coming second. Okay, so what were your thoughts about how we can try to prove that it's injective?
Minus B1.
I'm sorry?
Minus.
So we can subtract. So this implies phi of x minus phi of y equals 0, and that's the 0 in k, or phi of x minus y equals 0k, as phi is a ring homomorphism. Do you think that this is a good thing to be using? Do you think the fact that phi of a sum is the sum of the phis, or phi of a difference is the difference of the phis, do you think that should be coming into the proof somewhere?
Maybe.
Well, what are the conditions of the theorem? The theorem is that the phi from f to k is a ring homomorphism. If I don't need that property, then I could actually make this proposition about a more general class of functions. So almost surely I want to use all three properties somewhere. We've already used 2 out of 3. So probably we want to use the third property, that it has nice properties, nice behavior with respect to addition. Again, this is just trying to give you a sense of how would I look at a problem like this. For the second one, it seemed natural that I would want to use multiplication. Maybe for the first one, I want to use addition somehow. So we know x minus y gets sent to the 0 element. Okay. So this means x minus y is in the kernel of phi. It's something that's sent to 0. So the question is, can there be more than one thing sent to 0? Can you give me something in the kernel of phi, something that you know is in the kernel of phi? 0. So we know 0, and that 0f is in the kernel of phi, must show nothing else. So do we know that the kernel contains only the 0 element? And again, that's essentially what it means to be injective. So if we know it's injective, we know that only 0 is in the kernel. And if we know that only 0 is in the kernel, then we know it's injective. Right now, we don't know either. We're trying to prove that it's injective. And so we know we have the 0 element. We have some new element x minus y. We want to show x minus y is equal to 0. So do we agree that x minus y is in the kernel? X minus y sent to 0. So let's assume x minus y does not equal 0. If it doesn't equal 0, what do we know about it? It has an inverse. Thus has an inverse as f is a field. Remember, all the non-zero elements have to have an inverse. When you're proving something like this at this level in your career, you should be using all the conditions in a theorem. If there's a condition that we don't use, probably we did something wrong. It's possible that we don't need the condition, that it just makes the proof easier, that there might be a more challenging, difficult proof where we don't use all the conditions. But at some point, we're using that this is more than just a ring homomorphism. This is a ring homomorphism between two fields. So somehow we should be using that f as a field. So here we're using that f as a field. Here we're using that it's a ring homomorphism. So what does this mean? So your x minus y inverse exists, and phi of x minus y times x minus y inverse equals phi of 1. And what does that equal? It just equals 1. But what do we know about phi of a product? Product of the phis. So as phi is a ring homomorphism, that gives us phi of x minus y times phi of x minus y inverse equals 1. Now, we've already done part B, so we actually have some idea of what phi of x minus y inverse is. But we don't need to know that. What do we know about phi of x minus y? It's 0. So we get 0, and that's 0 in k, times phi of x minus y inverse, I don't really care what that is 1. So 0 equals 1 contradiction. Yeah. Thus, x minus y is the 0 element, or x equals y, so it's it's injective. And I'll move the proof symbol down a little bit. So this is a nice proof. We're using all the properties of the ring homomorphism. We're using the fact that we have fields. And again, when you're trying to figure out how to do this, have a piece of paper and write down what are the givens. What do you know? As soon as I tell you it's a field, you should be thinking, what are the properties of a field? As soon as I tell you it's a ring homomorphism, you should be thinking, what are the properties of a ring homomorphism? The more of these problems you do, the easier it's going to be for you to figure out what's the correct order to connect all of these items. We have a lot of properties of being a field. We have a lot of properties of ring homomorphism. Which ones are going to matter? Which order do we want to do them? When I have a ring homomorphism, it's true for any x and y. Which ones do I want to choose? For part B, it was very natural to choose A and A inverse. Here, if we're trying to show that it's injective, it's natural to start off by saying, well, let's assume that two elements are sent to the same. Let's show that they must be the same element. And then we have two possibilities. I could multiply both sides by maybe like phi of x inverse or phi of y inverse, and use the multiplicative properties, or I could subtract and use the additive properties. Given that the second problem, part B, used multiplicative, probably this one is using additive. But imagine we tried to do it with additive and we got nowhere. Then we would say, okay, well, maybe that was a bad choice. Let's go back and let's try to think multiplicatively. And if that doesn't work, then we curse and say, all right, well, maybe the first one wasn't so bad after all. And maybe we can make that work. But the idea is to try to come up with a strategy of how to attack problems like this. And then we got that x minus y had to be in the kernel. We know that 0 is in the kernel. We want to show that there's nothing else. Notice that we used the fact that f was a field. Where did we use that? We used that to say that x minus y has an inverse. So do you think this proof would work in Z mod 12Z? So you might be able to find an example of a ring homomorphism, maybe from some ring into Z mod 12Z, that is non-injective. And that would be a great exercise for you to do. That would probably be a great exam question. Remove the assumption that F and K are fields. Show that you can come up with a ring homomorphism between two rings that's non-injective. Maybe both of them are not fields. Maybe one of them is a field and one of them is not. Whenever you have a theorem, remove a condition. And normally that either makes the proof much harder or the result is false. And so here, if they're no longer fields, the result is probably false. And we can see precisely where we're using it's a field. This is where we use it's a field. So here it's using field. Using field. Okay. All right, any questions on this proof? And again, this is the advantage of being able to flip the class. We can spend a lot more time really discussing how to prove something like this. Okay, so the next one is looking at some different sets. So the first set is a plus b squared root of 2 plus c squared root of 3, where a, b, and c are rational numbers. And the second is what we'll call q adjoint square root of 2 square root of 3. It's a plus b root 2 plus c root 3 plus d root 6. A, B, C, D are in Q. So we have two sets. Can anybody tell me the relationship between the two sets? So you have the set on the left and the set on the right. So when I give you two sets, what are the possible relations between the sets? So one could be a subset of another, or maybe they have an intersection, but maybe one is not a subset of the other. So if I give you something in the form a plus b root 2 plus c root 3, I can always find a choice of a, b, c, and d to have it in the second. What should I do? Yeah, just take d equals 0. So clearly the left is contained in the right. Is the right contained in the left, or do you have some elements that are not? So if we take d equals 1, so is the square root of 6 equal to a plus b root 2 plus c root 3 for some a, b, c? Does this look immediately clear? Can we find a choice of A, B, and C so that this will hold? Okay, so root 6 is root 2 times root 3. But when I look at my linear combinations, I'm looking at the linear combinations of 1 square root of 2 square root of 3. I don't have a product. So if a equals 0, we could square, and we would get 6 is equal to b root 2 plus c root 3 squared is 2b squared plus 3c squared plus 2bc square root of 6. So in this case, we would get 2bc square root of 6 is equal to 2b squared plus 3c squared minus 6, or the square root of 6 is 2b squared plus 3c squared minus 6 over 2bc, which is a rational number contradiction. So this is everybody comfortable that the square root of 6 is not rational? Has everyone seen a proof of this? Okay, so note, if the square root of 6 is in Q, then I can write the square root of 6 as P over Q. So without loss of generality, we can assume the GCD of P and Q equals 1. Because if P and Q are both divisible by 5, I can remove that from both of them. So everybody agree that I can always assume P and Q have no common factor. So now, if I square, I would get 6 is equal to P squared over Q squared, or 6Q squared equals P squared. So what can I deduce now? If 6Q squared equals P squared, I'm sorry? So I know 6Q squared equals P squared. So what do you know about the left-hand side? It's a multiple of 6. So what do you know about the right-hand side? So does 6 have to divide P squared?
Yes.
Why not? Well, I mean, why?
It's just Q squared.
So what? How can you deduce that 6 divides P times P?
Divide.
So we know 6 divides P squared, which is P times P. So what we can deduce from this is we know if a prime divides a product, then it has to divide at least one factor. Therefore, 2 divides P and 3 divides P as a prime dividing a product divides at least one factor. So we know that P squared is a multiple of 6. So I can write P, I'm sorry, so P is a multiple of 6. So I can write P as maybe 6 times U. So 6Q squared equals P squared becomes 6Q squared equals 6U squared is 6 squared U squared. What should we do to both sides? Well, I wouldn't take this. We've got 6Q squared on the left and 6 squared U squared on the right. What can we do to both sides? We can divide by 6. Thus, Q squared equals 6U squared. And a similar argument gives Q is 6 times V for some V. Thus 6 divides P and 6 divides Q violates relatively prime contradiction. So this is a proof that the square root of 6 is irrational. And you can modify this to prove lots of numbers are irrational. So does this show that we can't write the square root of 6 as a combination of these elements? No, it just shows we can't do it with a equals 0. You can similarly show you can't do it with b equals 0. You can similarly show you can't do it with c equals 0. But maybe there's a way to do it with some special choice of a, b, and c. So I'll leave this as an exercise for you to try to see, can you find a choice of a, b, and c? Or if you can't, prove that none exist. Okay? And this is explaining to us why we want to look perhaps at numbers or at numbers of the form a plus b square root of 2 plus c square root of 3 plus d square root of 6. If I want to take the square root of 2 and the square root of 3, and I want to add them to the rationals, and I want to have a field, well, a field is going to be a ring, so I've got to be able to add elements. I've got to be able to multiply elements, right? And so if I can add elements, that's going to give me all the things of the form b square roots of 2 or c square roots of 3. But if I multiply, I also get square root of 2 times square root of 3. So I have to allow myself to have something like the square root of 6. Then the question is there anything else I need? No, because if the square root of 2 hits the square root of 2, what do I get? So if square root of 2 hits square root of 2, what do I get? This is not hard. Square root of 2 times square root of 2 is 2. So I'm not going to get anything new. That can just be handled by a, the constant term. If the square root of 3 hits the square root of 3, what do I get? 3. I don't have anything new. That's again just the constant term. Similarly with square root of 6 hitting square root of 6. If the square root of 2 hits the square root of 3, great, that's just square root of 6. What if the square root of 2 hits the square root of 6? What do I get? Try again. Square root of 2 times square root of 6. Other way around. 2 root 3. And so that would just be changing what the value of b is. So what you can show is if you take anything of the form a plus b root 2 plus c root 3 plus d root 6 and you add it to itself, you're going to just get back something of this form. If you take two things of this form and multiply them, you'll get something of this form. Now here's the harder question. Will you be able to find an inverse? Will it have an inverse of this form? So the question is, showing that this is a ring is not that bad. We can show it's closed under addition. We can show it's closed under multiplication. These are all subsets of the real numbers. They inherit all the properties you want from the real numbers. The difficulty is, can we show that the non-zero elements have an inverse of this form? As a real number, as long as this is not 0, will it have an inverse? Yeah, but that inverse may not be of this form. So as an exercise, try to show two things here. And again, I might do some of this in section 2 today. Show that this linear combination on the right is invertible if a, b, c, and d are not all 0. And that its inverse is also going to be of this form. And then the second one is to show that I can't write square root of 6 as a combination of just 1 square root of 2 square root of 3. I really need all 4 basis elements: 1, root 2, root 3, and root 6. And again, if I'm trying to form a ring or a field with the square root of 2 and square root of 3, think of it as a game. I am a cheapskate. I'm adding in the square root of 2 and the square root of 3. What is the smallest amount of things I need to add to make this into a ring or a field? Well, once I add the square root of 2, I have to add in all multiples of root 2. Once I add the square root of 3, I have to add in all multiples of the square root of 3. Then I have to add all sums of these. But unfortunately, I also have to add their product. So I also have to add the square root of 6. What's nice is as soon as I do that, no more sums, products, whatever I look at, none of these is going to generate anything new, anything outside of this form. But the question is, maybe there's a really clever way of writing the square root of 6 as maybe it's, 17 minus 21 square root of 2 plus 3 square roots of 3. I'm just making up numbers. I have absolutely no idea, right? Maybe there's some way to do that. We just showed here that you can't do it if A, B, or C is 0. Okay, well, maybe all 3 of them have to be non-zero. So these are things to think about and try. The set on the right clearly has nice properties. And so when we adjoin two elements like square root of 2, square root of 3, this is what we mean. We mean all combinations. But maybe it can be written more concisely. Maybe we don't need the square root of 6. Okay. So let's look at the finite field FP. So this is extremely important. We're going to see this all the time. So this is, oops, that's incredible zoom in. Okay. So we're looking at FP. Going to be, Z mod PZ. And since we want the field, I look at the multiplicative elements. So like this. So I'll write it like this. So these are the invertible elements. So everything but 0. And then, Z mod PZ is the ring. It's Z mod PZ star union 0. And we've talked numerous times about why the non-zero elements are invertible. So what is the key ingredient in the proof? I'm sorry? What's the key ingredient in the proof that the non-zero elements are invertible? What's the key ingredient in proving that if I choose something relatively prime to P, it has an inverse, a multiplicative inverse? Yes. What is that called? I use the Euclidean algorithm, right? The key fact is, Euclidean algorithm. If the GCD of A and P equals 1, then there exists X and Y such that AX plus BP equals 1. So AX equals 1 mod P, so A is invertible. So here's an interesting fact. If I look at X plus Y to the P, how would you evaluate that? What would you use to calculate X plus Y to the P? We could, but just going back to what you would do before you took abstract algebra, how would you calculate X plus Y to the P? Let's just say X and Y are just any real numbers or complex numbers. How would you calculate X plus Y? How would you calculate X plus Y squared? You do FOIL. How would you do X plus Y cubed? continue. Do you remember what's called, what theorem gives us the expansion? Binomial theorem, right? This is the sum, k goes from 0 to p, of p choose k, x to the k, y to the p minus k, with p choose k equals p factorial over k factorial p minus k factorial. So the first term is going to be x to the p. Then we'll have a sum, k goes from 1 to p minus 1, of p choose k, x to the k, y to the p minus k, plus y to the p. So let's look at Pascal's triangle a little bit. So it's 1, and then the next row is prime. Oh, so this is the 0th row. So the next row is 1, 1, then 1, 2, 1, then 1, 3, 3, 1. The next row is not a prime. 1, 4, 6, 4, 1. The next row is prime. 1, 5, 10, 10, 5, 1. Next row is not prime. 1, 6, 15, 20, 15, 6, 1. Next row is prime. 1, 7, 21, 35, 35, 21, 7, 1, and so on and so on. We care about the stuff in the middle. It might be useful. So when I look at x plus y to the p, I get x to the p plus y to the p. And I can do this for any p, but if p is prime, there's something really interesting about the stuff in the middle. What do you notice? I've got 2, 3, 3, 5, 10, 10, 5. What do you notice about 5, 10, 10, 5? It's symmetric, but here, let me give you the rows. This is row 0, row 1, row 2, row 3, row 4, row 5, row 6, row 7. In row 2, I have 2 in the middle. In row 3, I have 3, 3. In row 5, I have 5, 10, 10, 5. In row 7, I have 7, 21, 35, 35, 21, 7. Yes, they're symmetric, but there's something interesting about those numbers and the row. They're multiples. Is that true for rows 6 and 4? No. But it seems like if I have a prime, every element in the middle is a multiple of the prime. And so it turns out that this is always a multiple of p. How many of you have seen this before, this wonderful property? So when you look at quantities, it's nice to know what kind of objects they are. What can you tell me about a binomial coefficient? If I tell you something's a binomial coefficient, what kind of number is it?
Polynomial.
So I'm giving you a binomial coefficient. Binomial coefficient is not a polynomial, right? What kind of numbers? The binomial coefficients, these are the numbers appearing in Pascal's triangle. What kind of numbers are all of these? So what word would you use to describe these numbers? These are integers. Are any of binomial coefficients fractions? No. It's how many ways can I choose 3 objects from 5? I'm counting things. These are all integers. P choose k, which is p factorial over k factorial p minus k factorial, is an integer. And p divides the numerator, but not denominator, if 1 is less than or equal to k is less than or equal to p minus 1. So clearly, p is going to divide the numerator. Since k is less than p, k factorial is not a multiple of p. Since k is at least 1, P minus K factorial is not a multiple of P. So P choose K has to be a multiple of P if P is a prime. So we get, if P is prime, then x plus y to the P is x to the P plus y to the P. Let me see if I can. So we just showed x plus y to the P equals x to the P plus y to the P if P is prime. Can somebody give me a good choice of x and y? Simplest choice of x and y that might be interesting.
1.
And
1.
1. Perfect choice. So if x equals y equals 1, we get 1 plus 1 to the P equals 1 to the P plus 1 to the P mod P. And this is mod P, sorry. So 2 to the P equals 2 mod P. Or 2 to the P minus 1 equals 1 mod P if P does not equal 2. Now that we have x equals y equals 1, what would be a good choice next? If x equals and y equals. So we've just calculated 2 to the P. What do we want to calculate next? 3 to the P. So how should we get 3 to the P? Excellent. Do you see how we're just building up? So now we would get 2 plus 1 to the P is equal to 2 to the P plus 1 to the P mod P. So 3 to the P. Now what does 2 to the P equal mod P? 2 plus 1 mod P. So 3 to the P equals 3 mod P. So 3 to the P minus 1 equals 1 mod P if P does not equal, let's say 2 or 3. So we've basically been able to invert. And we can just keep marching down. So what have we essentially proved here? What theorem are we basically proving right now? I'm sorry? Yeah, but there's a famous theorem, 2 to the P minus 1 is 1 mod P if 2 is relatively prime to P. 3 to the P minus 1 is 1 mod P. Yeah, this is basically from Oz little theorem. Now, building on our success with 1 and 2, what should our next choice for x be? So what would the next choice of x be? I'm sorry? You could do 2 and 2. I don't like doing 2 and 2 though. 3 and 1. I like 3 and 1 much more than 2 and 2. Right? You could do 2 and 2, but after 3 and 1, what would you do next? Yeah, I would do 4 and 1, and after 4 and 1, what would I do next? 5 and 1. I would just keep marching down like that. I would always keep y to be 1 and increase x. How would you prove this formally? What would you use? Induction. So this is screaming, please prove me by induction. right? So it's a good way, I strongly urge you, try to prove this by induction. And so, take some prime and show that for all the stuff less than that number, we have Fermat's little theorem. Now, you could try to do 1 plus 1 plus 1 to the p instead of 2 plus 1 to the p. That's perfectly fine, right? As a hint, one way to do this is if I give you x plus y plus z to the p, do we agree that this is just x plus y to the p plus z to the p mod p? Why is that true? Yeah, so instead of using x plus y, I could use a, b, and c, and then x would be a plus b, and y would be z. But then what do we know about x plus y to the p? X to the p plus y to the p plus z to the p mod p. So if we wanted to, how could we write n? And instead of doing this 2 plus 1, 3 plus 1, 4 plus 1, 5 plus 1, what could we do? One plus 1 plus 1, just do 1 n times. So depending on how you're doing things, sometimes one way might be a little bit better than another. So I could write 3 as 2 plus 1. I can write 3 as 1 plus 1 plus 1. I can expand what I'm doing, and as long as I only have a finite sum, both of these approaches are fine. Maybe one works better than another. It's nice to be aware of both of them. And this might be useful for one of the homework problems. You can, I think, do it without doing this, but it's not bad to just explicitly talk a little bit about this. So this is giving you some nice consequences of looking at these fields. We're getting Fermat's little theorem here, and we're also seeing really good ways of attacking problems and proving things. We're also seeing the advantage of being lazy, right? Once we've proven x plus y to the p is x to the p plus y to the p mod p, then we can extend this from a sum of 2 objects to a sum of 3 objects. I will do the following. Oops. Oh, shoot. I unfortunately chose to copy something that had information on it. So I will do this just because this always bothers me. It's not really done well in calculus. How many people remember their calculus? So calc review. What's the derivative of a sum? Sum of the derivatives. Now, it's not necessarily true if you have an infinite sum, but if we have f of x plus g of x, oh, here, let me use better notation. I'll use f1 of x plus f2 of x plus f3 of x. Almost surely when you took calculus, they proved, if you were lucky, that the derivative of a sum of 2 functions is the sum of the 2 derivatives. And I doubt they proved that this is true for the sum of 3 or the sum of 4 or the sum of 5 functions. How would we prove, knowing that the sum of 2 functions, its derivative is the sum of the 2 derivatives, how would we prove the derivative of a sum of 3 functions?
Can you do it like how you were just doing a second ago, like grouped together?
Yes, foreshadowing, the art of a good lecture, right? It's exactly the same idea. It's f1 of x plus f2 of x, put that in parentheses, plus f3 of x, and now we have a sum of 2 functions. And so now this is just the derivative of the first, f1 of x plus f2 of x prime plus f3 of x prime. Now, the first one, oh, well, that's just the derivative of a sum of 2 functions. We use our rule again. This is just f1 prime of x plus f2 prime of x plus f3 prime of x. And now we drop the parentheses. And why can we drop the parentheses? What do we know about addition? It's associative. It doesn't matter how I write the sums. It doesn't matter how I group them. So this proves the sum of the derivative of a sum of three functions is the sum of the three derivatives. And by induction, you can prove that the derivative of the sum of any finite number of functions is the sum of the finitely many derivatives. But we cannot prove that it is true if you have an infinite sum. So if you have an infinite sum, it may not be differentiable. Okay? And so it might be interesting, can you come up with a example where the function is written as a sum of infinitely many functions. Each one is differentiable. But maybe the function is not the sum of the derivatives. Maybe the function is not even differentiable. So here's an extra credit challenge. Find a function f of x such that f of x equals the sum and goes from 0 to infinity fn of x. Each fn of x is differentiable, but f prime of x is not the sum and goes from 0 to infinity of fn prime of x. There's many reasons why it may not equal the sum of the derivatives. One might be maybe f is differentiable, but maybe the sum doesn't converge. Or it could be maybe f is not differentiable. The sum might converge, but f is not differentiable. So there's many ways this can fail. So the point here is to just alert you to some things to be aware of. Okay, so next is just continuing some more definitions. It's been a while since we've had some definitions. Let K be a field. A subfield of K is a subset F of K that is itself a field using the same rules of addition and multiplication. This should be a no-brainer definition, right? This is just like a subgroup is a group in its own that lives inside a bigger group. A subring is a ring that lives inside a bigger ring. Can somebody give me a subfield of the field I'm thinking of? There's always a natural subfield. So I'm thinking of some field K. Give me a subfield of K. So what would be the identity? So then that wouldn't have the zero element. So 1 plus 1 would not be necessarily in it. Itself, right? It doesn't say it has to be a proper subset. So always think of these, trivial counterexamples. It's possible that, F might be K. And then you could consider, just maybe the zero element. Are the non-zero elements invertible? Well, there are no non-zero elements, so the question is, when are there non-trivial subfields? And then instead of going with a field and trying to find something which may be smaller, we could go in the opposite direction and try to find something that might be larger. And so an extension field of F is a field K such that F is a subfield of K. So I might email the author, maybe we should use a different letter. So we have one letter if it's a subfield and another letter if it's an overfield or an extension field. So let's think of some field. So here is R. Do we all agree that R is a field? Can somebody give me a subfield of R other than R? Q. So the rationals would be a subfield of R, and it's not equal to all of R. Can you give me a extension of R that's more than R? See the complex numbers. Now, there's more than one possible subfield, or sometimes there's more than one possible extension field. So for example, let n be square free, and let's consider q square roots of n is going to be all things of the form a plus b root n, where a and b are rational numbers. So we're looking at all things of the form a plus b root n. So do you think this is a field? What's the only property that might be difficult? If you want to show that this is a field. I'm sorry? The inverse. Does this have an inverse? If I give you something in the form a plus b root n, if it's not 0, does it have an inverse? Yeah, it's a real number. It has an inverse. The question is, does it have an inverse of this form? So let's set a plus b root n does not equal 0. And since n is square free, if a and b are not both 0, then a plus b root n is non-zero. So that's a good thing for you to try to show. So we want to try to find an inverse. In q square roots of n. So if I give you a plus b root n, in mathematics, there's two ways to do nothing. I can add 0 and I can multiply by 0. Hopefully you remember from algebra 2 or algebra 1, a good way to multiply by 1 here. A minus b root n over a minus b root n. This is called, like rationalizing the denominators. But I want to do something like this. So I'm trying to find an inverse for this. So rather than looking at it like this, let me look at it like this. Can you write me a real number for the inverse of a plus b root n? Well, I know its inverse is the real number 1 over a plus b root n. And now I multiply that by a minus b root n over a minus b root n. I know what the inverse is, right? It's just 1 over my number. And so now when I do this, the numerator is a minus b root n. What's the denominator? So a plus b root n times a minus b root n, what would that equal? A squared minus b squared n. And so since n is square free, you can show that the denominator is not 0. So the inverse, I can write it as a over a squared minus b squared n minus, I'll do plus negative b over a squared minus b squared n square root of n. A squared minus b squared n is not 0. This is in q adjoint the square root of n. So we've just shown it does have an inverse. So what this means is we actually have another field. Q square root of 2. So that's larger than q and smaller than r. And so it's an interesting question to try to figure out what are all the possible extension fields in different setups. All right, so this is a good place to stop. I gotta go get some stuff.